So we are back to a very traditional topic now about the density-based clustering technique. So we all know about the density-based algorithm DBSCAN. This is a fundamental density-based clustering technique which bases on the cardinality of the neighborhood object for presenting the notion of density. So in DBSCAN, this is the density-based clustering technique. They assign for each object a property including a curve, a border, or a noise based on the cardinality of the neighborhood and use them for producing cluster. For example, an object is a core if it has more than each object inside its epsilon neighborhood. So we draw the circle around and then we count how many objects inside the circle. If it exceeds the me, then this is a core. So an object is a border object if it is not a core, but one of its neighbors is a core. Otherwise, they call this a noise object. So DBSCAN had very long traditional, I think more than 20 years old now, and they have many applications. Currently, for example, detect grouping population of province in Canada, or they identify the source of gamma rays in astronomical images, and they detecting landslide hazards in Taiwan, or for example, they group trajectory of aircraft and discover some unusual pictures in the skin. So generally, how do DBSCAN produce cluster? So they just randomly pick an object, and then they perform the rank query around it, and then they check if this is a core. If it's a core, then they put every object inside the neighborhood into the exit list, into a list they call the seed list, and then they randomly extract an object from the list, and then they perform the rank query around it again, and put every object inside the neighbor into the list until the list is empty. By this way, they can discover cluster with arbitrary sub. And the procedure continues until the seed list is empty. So one major drawback of DBSCAN is that if you have n object, then it requires O(n) number of rank query to build cluster. And moreover, they suffer from several problems that we describe in the next slide. So for this scalability problem, so given a data set like this one, then in order to find cluster, then DBSCAN needs to perform the rank query on all objects. So if the number of objects is too high, then the runtime is also quite very high. So the problem here is, can we detect the red and blue cluster without having to perform the rank query on all objects like DBSCAN for saving runtimes? So here we have solution. If we let the algorithm learn itself which objects are the most important to build cluster, then we can produce the red and blue cluster with only, for example, in this case, if they choose A, B, C, D, E, and F, with only 6 rank query, they can discover the true cluster. So the second drawback is that the batch processing, that means DBSCAN runs from start to the end and only produces one cluster. And during its runtime, there is no interaction. That means user cannot interact with the algorithm, or if they want some approximation results, they cannot do it. So our solution is that we convert the DBSCAN into an anytime technique. So generally, our algorithm quickly produces an approximate result, and then they continue refine it during further runs until they reach the final result of DBSCAN. For example, you see here we have an example data set. If we run it for 1 second, then we have many clusters like this. And the more time we have, the better the clustering result we have. Until, for example, if we run it to 7 seconds, then we almost found all cluster exactly. So another problem is how to deal with complex data. Many existing techniques for speeding up DBSCAN generally relies on the grid scheme. So they build a grid and then they cluster points inside every grid cells locally for saving runtimes. But this will limit the technique to only vector data. And if you want to work with some complex data, for example, if you want to work with trajectory or you want to work with images, there is no way to do it. So in our work here, one basic technique is that we use the rank query as a primitive task, and except the rank query itself, we do not use any additional technique, for example, grid. So our algorithm can fit well with arbitrary kind of data set, for example, trajectory. Another problem is that DBSCAN is very hard for parallelizing. So nowadays we have multi-core processor available here. And how can we exploit the multi-core processors for speeding up the DBSCAN is also a question, and also we will address this in this approach. So generally our algorithm we call anytime DBSCAN or AnyDBC consists of 9 main steps. So it's first summarize object into small group called primitive cluster. Then they try to build a connection graph that connects the primitive cluster together. And during its execution, the cluster can be found by following the connected components inside the graph until there is no more changes in graph. The major approach here we mentioned is the active learning technique in step 6, where the algorithm will examine the graph and then choose the object that is most important. That means they can help to discover cluster faster and only perform the rank query on these objects for speeding up the processing. So we demonstrate our techniques based on the toy dataset here, which contains 2 clusters, the blue and the red one, and one noise is we denote by the black dot. So in the first step, this is a summarization step here. Because our technique do not use all the rank queries for processing the object, so instead of the core, the border, and noises property of an object, we have more properties. So we separate them into 2 based on this picture. So we have a processed and unprocessed object. And for example, if object is processed core, that means a rank query had already been done on this object. If object is an unprocessed, that means, okay, we didn't do the rank query on this, but we know this property. For example, if we know that, okay, they have more than V points, then they will be a core object, though we did not perform any rank query on it. So based on the so-called object transitions that we just summarize our the smaller cluster. We randomly pick some objects, for example, I here, and then we perform the rank query around I, and then we mark all objects inside I at unprocessed border. Because actually we didn't do the rank query on the blue object, but we know that it must be a border of a red object, so we summarize them into smaller group. And then in the next session, we choose some white object. That means we never touch them, and then we continue to perform the rank query. For example, this time we choose B. And then we perform the rank query around B, and then we mark the core property of all objects. So we have B is core, and then some blue. And for every small group like this, we call a primitive cluster, and we push them into the list of primitive cluster for further processing. Now we come to specific object. For example, G, this is a noise object. We have no neighborhood, so we put them into a separate list for a post-processing step. We call the noise list. And we do it until there is no more object, no more white object. So in the step 2, we create a connection graph that we represent the connectivity of some primitive circle that might the way they might connect it to form cluster. For example, for the primitive cluster B and C here, because the distance between B and C is too high, for example, in this case bigger than 3 epsilon, then they will never be density connected. So we denote the connection at the node. For primitive cluster A and B, because they are close enough to each other, they might be density connected if we do some additional rank query, but we do not know for sure. So we mark the connection between them is weak. That means they might be connected, but we do not know. For C and D, for example, they have a white object. The yellow object here, we do not perform the rank query on it, but we know this is a core object. So it will connect C and D together into the same cluster. So we mark the connection between C and D. It means yes, that means they will surely be connected together. So in step 3 and 4, we try to find connected component and merge cluster to merge them to find cluster. In this case, for example, we have a lemma that on collecting the component of primitive circle by the Z state will belong to the same cluster. So in this case, C and D will surely belong to the same cluster, so we merge them into a big cluster. And after merging, we need to set up the new connection between CD and IB, because actually we merge many nodes together. In this case, we have, because the connection between C and D are no, then the connectivity between the big cluster CD and I now also be no. And similar, B also connect to CD by the no state. Note that we remove the no state for more clarity. So then we need to see, the most important is how can we know that we should stop the algorithm. So we can prove that, okay, when there is no weak connection in the graph, then now we can safely stop the algorithm and we acquire the same result with DBSCAN. If we do not stop the algorithm and we continue to run, then there is no more chance in the clustering result and we waste time. So in this case, we still have one weak connection between A and B, so our algorithm must continue. So we go to step 6, how to select object for performing the rank query. This is the most important aspect in any DBSCAN. Because, for example, if we choose the wrong object, for example, if we choose X and perform the rank query without it, then there is no change in the cluster structure and we watch one rank query. So now, but if we choose E, for example, then we perform rank query around E, and we know that, okay, E is a core object. Then A and B will be density connected together, and then we discover the true cluster, and now our algorithm can stop without doing further rank query. So a naive scheme is that we randomly choose object for querying, but this is very inefficient. So in our approach, we propose an active learning scheme to let the algorithm grant the object based on the statistical information of every primitive cluster and the status of objects inside primitive cluster. So this is quite very complicated, so we only briefly describe the idea here. And then we choose some object with the highest score for performing rank query only and leave the other object for further step. So now we have some object to perform the rank query. We need to perform the rank query on them. For example, in this case, they choose object E for performing the rank query. Then we perform the rank query on E, and then we merge the neighborhood of E into the cluster A and B, because E belongs to both the primitive cluster A and B. And then we need to update the graph, because now we perform some rank query and some object have changed the core property, so we need to reflect the change. So now the connectivity between A and B now will become yes, because we know that E is now a core object, and it will connect A and B together by the density connectivity. So the algorithm repeats from the step 3 until there is no more weak edges in the graph, and then it stops. But now we still have to proceed outline. Remember, in the first step, if an object is an outline, then we put them out and into a noise list for further processing. Some of them might be a true outline, some of them might be not. They actually be a border object of some cluster. For example, G is surely a core object, a noise object, but this is actually a border object because one of its neighbor is F. This is the core object. So we discover such kind of border objects for. So we can prove that, okay, the final results of AnyDBC are completely identical to those of DBSCAN. So now we come to the experiment where we demonstrate the performance of our technique. So we created some synthetic data set, and then we create much bigger data set by duplicating some object. So now we have some data set which have from 500,000 to 3 million objects, and they are in from 16 to 32 cluster. So in the first picture here, we saw the final cumulative runtime of AnyDBC of our technique, and this is the x coordinate is the number of objects. So we see that when we have more objects, the runtime will increases. But in the next picture here, we saw the final speed up factor compared with DBSCAN. So we see that the higher the number of objects, the bigger the speed up factor we get. The reason is because we summarize objects into smaller groups. So if we have high density object, then they mostly lie into one smaller group. So we save a lot of runtime. So we explain why the AnyDBC is faster than DBSCAN in the third picture here. You can see that, for example, for 3 million objects, our technique, AnyDBC, only use 7,000 rand query instead of on 3 million rand query. And this is less than 0.25% of number of rand query. That's the reason why AnyDBC is much faster than DBSCAN. So there is another interesting property, that is the anytime property of AnyDBC. So in this one, we see the crowd chart, and we have the runtime here. We see that, algorithm start with only, for example, for the red curve, start with only 4 seconds. And then the more time we have, the better the clustering result we have until we reach to the final result with NMI score equal 1. That means we produce exactly the same result with DBSCAN. So in the picture below, we see the clustering results on the corpus callosum dataset. This is the biggest fiber dataset that connect the left and right hemisphere in the branch. So we see that, if we stop the algorithm right after step 1, we have 30 clusters, but the more time we have, the more the cluster will be merged together, and until at the end, they come to the final results of DBSCAN. So one thing we want to evaluate is that how is the efficiency of the ranking scheme of AnyDBC compared with the randomized scheme. So we see that we have the red line here is the AnyDBC, and the blue line is the random scheme. We said if we choose object randomly, then we need much more rank query than we using our ranking scheme. So we see that our ranking scheme stop very quickly, less than 5 iterations, while the random scheme require more than 200 iterations. So we have a performance on the real data set here, where we compare our technique with DBSCAN, and the fastest variant of DBSCAN we call DBSCAN Art until now. So we see that, for example, for gas sensor data with epsilon equals 6,000, our technique requires only 70 seconds, and it is around 90 and more than 200 times faster than DBSCAN R and DBSCAN, which requires maybe 16,000 seconds at the end. And if we stop our algorithm earlier, for example, if we stop right after the step 1, we still have a very good result as we demonstrated in the first experiment, then the speed up factor will be much higher. And overall, our technique is orders of magnitude faster than rival technique. Yes. Okay. So now we go to the parallel processing on multi-core CPU. So we see that one very interesting property of our technique is that it is a parallel technique and anytime at the same time. So that means we can use multi-core for produce approximate results faster. And at the end, we still have very good scalability compared with the number of threads we use. For example, here for the gas sensor dataset or the palm up dataset here, we almost acquire very close to linear speed up factor compared with the number of threads. And for example, if we use 16 threads on the palm up 2 dataset here, we acquire 13 times speed up factor compared to the single thread uses. And the most interesting is that AnyDBC is the work efficient parallel technique. For example, for existing parallel technique here, they only perform all the rank query similar to the way DBSCAN did. So actually, they much lower than our technique. Yeah, and for conclusion, so our technique is an anytime technique, and this is parallel processing technique at the same time. Thank you.
Thank you very much. This, I mean, the general idea is that you have this anytime algorithm that converges to the correct result of DBSCAN. Do you have any way to measure the quality of the approximation? So basically, can you tell me at a certain, if I want to reach a certain approximation quality, can you tell me how long I have to iterate to reach that?
Yes, this is very good and very hard question, because measuring the clustering quality is right now an open question. So it's really hard to say if you want a clustering quality of some quality. But if you want, for example, you want to have some specific number of clusters. For example, if you want DBSCAN produce 6 clusters, but you want maybe 10 clusters, then you can stop whenever you see that our technique produces 10 clusters.
Yeah, that's definitely an approach. Yeah. Do we have any further questions or comments?
Maybe you could use the number of weak links somehow to estimate the current quality, or to estimate how much information the algorithm is still missing. Do you think this would be possible?
Yeah, I think this would be a very nice option.
Okay.
Yes.
Okay, thank you once more.